Hello, ladies and gentlemen. Welcome back. Before we get into our main section today, let's define a word. In order to truly understand what we're going to look at today, we need to understand what the word implicitly means. And I've copied a definition here. It's implied or understood, though not directly expressed. Or it's contained in the nature of something, though not readily apparent. So I've given two equations here. One of them is explicitly defined. The other one is implicitly defined. Which one do you think it is? Which one is implicit? I hope you're saying the one on the right is the implicitly defined function because the definition of y is contained within this function, though not explicitly stated. If we're going to find the derivative, find dy dx, the explicitly one is what we've been talking about. Dy dx is equal to, now we use the power rule, 6x squared minus 7. Easy peasy. Over on this side, it's a little bit different. If I differentiate the way that I've come to know to differentiate, we're going to get 2x plus, well, maybe 2y equals 0, and, well, there's not a dy dx. And that means that we've done something horribly wrong. This is not good, and this is what we're going to be looking at how to deal with today when the equation isn't written as y equals. How do we find dy dx? How do we differentiate? So we're going to go back to our chain rule, and we're going to find dy dx here. So dy dx is equal to, bring the 4 out in front, so 12 times what's inside to the third. Now we multiply by the derivative of what's inside by 2. Okay, now let me rephrase this. I'm going to say y is equal to 3 times, we'll call this g to the 4th. I'm letting g equal 2x minus 1. Now if I'm going to follow the same differentiation steps as I did in red, dy dx is equal to 12g cubed, but then I multiplied by the derivative of that g with respect to x. That's what the 2 is here. dg dx, if I want to take this and differentiate with respect to x, that's going to be equal to 2. That's where this guy comes from. So what we're doing is anytime we come across a variable that is different than that which we're differentiating with respect to, we need to multiply by its differential, it's called, by dy dx or by dg dx. And that's our implicit differentiation, it's called. So let's do an example. Let's find the gradient of the circle, x squared plus y squared equals 1 at the point 0, 1. Now, just for fun, x minus h squared times y minus k squared equals r squared is the equation for a circle, where its center is h, k, and its radius is r. So this circle right here is actually our unit circle. It has a center of 0, 0, and a radius of 1. We want to find the gradient of the circle at the point 0, 1. Now, if you know this is a circle, if you can envision the unit circle, envision where the point 0, 1 is, hopefully you know in your mind that, well, the gradient there is 0. But let's do it using some calculus. One way we could do this is solve for y. But I don't want to take the time to do that. I just want to get in and differentiate. It's so much fun for me. So here we go. We're going to differentiate the first term, 2x, plus differentiate the second. This is where we're kind of using that chain rule. We're going to do 2y times the differential dy dx. Because we're taking the derivative of something squared, but then we have to take the derivative of that something, and this equals 0. Now there's two ways to proceed from here. Some people would say, well, solve this for dy dx right now, then substitute your value for x and y and solve for dy dx. I prefer to substitute first, then solve for dy dx because it gets rid of all the extra other variables, and I think it makes it a little bit smoother to get dy dx alone. So 2 times 0 plus 2 times 1 times dy dx equals 0. So we have 0 plus 2 dy dx equals 0 dy dx. The gradient at the point 0, 1 is 0, just what I was expecting. If the problem hadn't said to find the gradient at a specific point, and it just said find dy dx, of course I would need to solve this for dy dx at this point here and isolate that differential. Alright, so here is our next example. I want to find dy dx for this equation. And notice that this is not a function. We can see that on the graph. This fails the vertical line test quite nicely. It's called the folium of Descartes. I want you to pause the video and see if you can find dy dx for this using implicit differentiation. Give it a try. Alright, so we're back. Let's give this a go. We're going to start differentiating. So 3x squared, nothing funny there, plus 3y squared times dy dx, implicit differentiation, minus, oh, now here is someplace, I hope you were careful, this is really product rule time. We have x times y. Those are two functions. We have x times y, which is a function of x. I'm going to just pull this 9 there. It's a constant. I don't have to leave it attached to the x or to the y. Now it's first times derivative of second plus second times derivative of first. Okay, so that's where hopefully you got before we start doing the algebraic manipulation. So we're going to simplify and solve for dy dx. So we want all the terms that have dy dx on one side, all the terms that don't on the other. Remember, the reason we want all the dy dx's together is so we can factor out that differential. So there's my rearranged equation with my differential factored out. Now we divide, and dy dx will be alone in all of its glory. And if you got this, kudos to you. If not, that's okay. We're still learning. I have one more example that we're going to look at today before we get up on out of here for the day. Now, we should all be able to do part A. I don't care if you know zero calculus. You should be able to do part A. We're calculating m using this point. We're going to substitute. Substitute 2 in for x and solve for y, or in this case, m. So we have 8m, 3m squared equals 16. This be a quadratic. Which is actually a factorable quadratic. And we get m is equal to 4/3, or m is equal to -4. And since m has to be negative, m is -4. And now that we know that, we can find the gradient of the normal to the tangent at P. Whoa, wow, that's intense. Gradient of the normal to the tangent, what does that mean? Well, what that means is if we have a curve, there's the tangent, the normal will be perpendicular to the tangent. So perpendicular. So we need to find the derivative. Pause the video, differentiate. There is a product rule that needs to be used here. Ready, set, go. And you should have this as your derivative. And here is where I might differ in how I proceed compared to other people. But I'm going to substitute my x and y's in right now and then solve for x and y. And here we go. We have 8 dy dx minus 32 plus 24 dy dx equals 0. Again, get everything that has a dy dx on one side, everything else to the other. We have 32 dy dx equals 32, so dy dx is equal to 1. Now, how does the slope of something perpendicular to that look? Well, that's going to look like the opposite reciprocal of our dy dx. So the slope of our normal, at P is -1. And there we go. Good to go. Implicit differentiation. The thing you really need to watch out for are places such as this, where you have to use the product rule. And with that, I'm out.